record, and that reminds me that I need to post the reading material for Module 8, which is going to be from Chapter 7 of Meyer. So it's kind of a little wonky, right? Module 8 is in Chapter 7. Okay? And, there'll be some of my own materials in there, but so Meyer Chapter 7 should cover most of the stuff we're going to be talking about before we go into the FPGA stuff, which the textbook does not cover at all. Okay? So, now let's talk about numbers versus numerations. So, okay, if you know the answer already, that's okay. But so the definition of numbers is kind of weird because you don't really usually think about it, right? We use number 1, 2, 3, 4, 5, all the time, without really think about, what's the etymology of these words that we use, right? So numbers are values of things, right? So if you have 12 apples, for example, physically there are 12 distinct apples somewhere, right, that you're talking about. Okay? And that number 12, right, is that number, okay? No matter what language you say, right? You can say it in Spanish, you can say it in Chinese, you can say it in binary, hexadecimal. That value stays the same. And so a number is actually a value of something. That doesn't change based on how we refer to it. Okay? So, and this thing I'm saying 12, right, this word itself, right, the word itself is actually what's known as a numeration. Okay? This is how we refer to this particular number. Okay? So in English, this number is represented by the word 12, right? Or, 10 plus 2, whatever it is, right? Okay? So this is known as numeration. And in this class, instead of when we go into digital electronics, one thing we have to learn is this thing called binary numerations. Instead of thinking about numbers, instead of base 10 numbers, right? Because we go from 0, 1, 2, 3, 4, 6, 7, 8, 10, right? And 10, we kind of move to the next digit, right? And in binary, what happened is that you only have 1 and 0. So by the time you count to 2, you have to move to the next digit already, which is kind of weird, right? To say the number, the word digit. Digit usually means 10 also. But that's what I should probably say is the place. Okay, so there's in decimal, there's the ones place, the tens place, the hundreds place. I don't have enough hands, so yes. The 100s place, right? So there's the ones place, the tens, right? The 100s, like the 1000s place, right? In each of these, the numbers in each of these places represent, 1 times 5, or 10 times 5, meaning 50, or 100 times 5, meaning 500, or 5 times 1,000, right? In binary, the places are ones, twos, right? Because that's the biggest number that a binary number can represent is actually 0 and 1. So the next place is actually going to be the twos place, okay? And then the next place is going to be the fours place, right? And then the next place is going to be the eights place, right? So these are all powers of 2, right? 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, okay? And what's up here is also the same thing, is base 10 power, 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, and so on like that, right? The math is the same, okay? And in order for us to do computation with a different numeration, right, all the math has to be consistent, okay? And this is what we're going to double check and learn about in binary math. How do we make this numeration so that all the math still works out, okay? So this is just a short example of what a binary number looks like. 0, 0, 1, 1. Oops, I read that backwards somehow. I complimented it. Sorry, let's not talk about complementation. 1, 1, 0, 1, okay? It's the same thing as if I was saying, 1,369, right? I would say this place first, and I will say the next one, the next one, the next one, right? So when I say this, it's 1, 1, 0, 0, okay? So this 1 represents a decimal value or a value of 8, okay? A decimal numeration with a value of 8, okay? Okay. This place here represents a decimal number of 4 with a value of 4, right? So the total number of this, oops, let's go to the ones and zero. The 0 means just 0 times 1, 0 times 2, right? So it has no value, has 0 values, okay? And therefore, when you add these numbers together, you get 12 instead, right? Same thing as if I add 1,000, so this is the same thing as, oops, let's erase this. Come on, erase. As 1,000 plus 300 plus 60 plus 9, right? That's the same math we're doing, right? So we're doing the same math, okay? We just want to make sure the math stays the same, okay? When you add this number together, it's 12. So 1100 is, the numeration is 1100. The value is 12, okay? So there's still 12 apples somewhere, right? No matter how you write it. Okay, so some definitions. The leftmost place here is called the most significant bit, right? The reason it's called the most significant bit, or MSB, you're going to see this everywhere, so just be used to this, is the highest value, right? Just like when I wrote this number, the MSB is 1,000, right? That's the most significant place, okay? Okay? And the one on the right is the least significant bit, okay? Right? So in the base 10 case, this will be the 9, right? So, but in this case, this will be the ones and 0. And it's not necessary for you to always go to the 1 place. Okay, you can actually crop this off, and this will only be able to represent even numbers, but it's, you may want that, right? And this is, if you don't have this place here, you can always represent any multiples of 4s, right? So you could crop these things off at different points. Okay, so the least significant bit is not always going to be the ones place. Okay, just be aware of that. Okay, so since we're dealing with digital electronics, we're going to be talking about binary numeration almost all the time in here. Okay, and that's because in electronics, we can always represent values of ones and zeros using either a low voltage point or a high voltage point, okay? Right? Where low means, oh, maybe around 0 volts, okay? And that's considered a binary 0, okay? Whatever is up here, right? Or it could be some sort of high voltage, a high level, not high, a high level of the voltage, meaning like maybe 5 volts, okay? And that represents a 1 in these places, okay? In fact, 0 to 5 volts is going to be what you'll be working with on the digital gates that you're going to be playing with. And this is known as the TTL family. It's a transistor something level. Transistor something level. Okay. Oh, you can look that up and figure out what that means, okay? All these acronyms are interesting, but not memorable, let's say. Okay. So if you were to convert a decimal number up to 7 to a 3-bit binary number, so when I say 3 bits, there are 3 places, right? Okay. 0 converts to 0, so hopefully we can all do that, right? 1, right, since we want a value of 1 in the ones place, then it's 0, 0, 1, okay? You still need to read out the 001 because it tells the whoever you're talking to, this is actually a 3-bit number. If you say 0001, it's actually a 4-bit number that can go up to a value of 15. I know this is not necessary right now, but it will come in useful when we start talking about negative number, right? We actually need to know how many bits these numerations are representing, okay? All right, and then 2, hopefully you can see this is, 0, 1, 0, okay? I'm not going to read them all out, but then When you get to 7, right, that's where you get 1, 1, 1, because this is the highest number you can represent in the binary states, right? Ones, right? This is when, well, all of this is the highest value 3 bits can represent, because it's 4 plus 2 plus 1, that gives you 7, right? And that's the highest number you can get. Okay? All right, so let's just do some practice. Okay, adding some numbers in binary. Okay, all right, so let's say I have a decimal number of 5 and then a decimal number 7, and that should add up to 12, right? Okay, you can see that I have a little subscript here under, subscript 10, subscript 10. Okay, in any electronic, digital, binary textbooks, okay, the default numeration is actually binary. When you don't have a thing, if you don't underscore it with 10, you should assume that it's actually binary you're talking about. Okay, so unlike other textbook where the default numeration is base 10, in digital electronics, the um, the default numeration is actually base 2 or binary. Okay, so that's why you see these little subscript 10s there, in order to tell you that, oh, this actually represents a number, a value, a number in decimal. Okay, so let's go back to, I don't remember when we did this, right? How to add two numbers together in decimal. Okay, so maybe like second grade, third grade, whenever we did this. Okay, all right, so I have to remind myself how to do this, right, every year. Okay, so when we add these two numbers together, we know it's gonna be 12, right? So we're gonna need two places to at least hold them, right? So I'm gonna represent 5 as 0, 5, right, and then 7 as 0, 7, because I know that there's probably gonna be an extra place here I have to deal with, right? Okay. So what I do is I add these two numbers up, right? Right? When I add those two numbers up, it's actually the value you get down here is 2, because, right, you cannot write 12 in a single place, right? So that's what we do here is we have a carry row where we put a 1 up here. Okay? You guys remember this? Maybe? It's been a long time, okay? And then what you do is you add the carry row plus the other two rows together. 1 plus 0 plus 0 is 1. And that's how you come up with the answer 12. Okay? Right? If you don't trust me, you can punch this in your calculator. Okay? I'm going to do the same thing in binary. Okay? If you convert 5 to binary, you get 4 0 1s, because this is 4 plus 0 plus 1, right? That's 5. Okay, 7 is 4 plus 2 plus 1, so therefore you get 7. Okay. Now, I think I need some space here. Push this over a little bit. Okay. Okay. All right. Now what I do is I do the same thing where I'm going to put an extra column just in case it goes over. Okay. I'm going to put 0, well, the 101 on top here, and then 111 on the bottom here. Since we're adding, it doesn't matter what order you put it in. Okay. Since addition is commutative. Okay. So I add 1 plus 1. What's 1 plus 1? 1 plus 1 is 0. Yeah. But then it has a carry of 1, right? Okay. 1 plus 0 plus 1 is what? It's also 0 with a carry of 1, right? And then 1 plus 1 plus 1 is what? It's 1 with a carry of 1 also. And then 1 plus 0 plus 0 is, of course, going to be 1, right? And this is exactly the same results we got up here, I hope, right? Yeah, let's just do it, right? So 101 plus 111 equals 1100, right? So this is supposed to be 5 plus 7, and then this place has a value of 8, this place has a value of 4, this place has a value of 0, this place has a, well, it has a value of 2, but it's multiplied by 0, and this place has value of 1, but multiplied by 0, so indeed that gives you 12, right? right? Yay, math still works. Okay, let's try a bigger number. Okay, you're gonna have more places. Okay, so let's add 139 plus 58. Okay, so 139 in binary, right? If you break this numbers down into, well, the way you break this down is to, well, 139, right? The next smaller power of 2 is going to be 128. Okay, you can do the math. You know that what that number is, and you just have to know what the powers of 2's are, right? Okay. Okay. So this will put you in the 2 to the eighth place, right? So that conversion places a 1 in the 2 to in the 2 to the eighth place. Okay. The rest of these are 0. You get 3 zeros because the next number you want is to be able to subtract 128 from it and still get a non-negative number. Okay, so that next value is 8, which is going to be in the eighth place, and the eighth place is the fourth, right? So the way you figure this out is that this is 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4s, right? Okay. Oh, no, you start at 2 to the 0. Don't forget to count from 0. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Okay. Right. So that's how you figure out where this place is supposed to be. Okay. And then now you have a value of 134, whatever. Wait, no. 136. Right. You add these two numbers, you get 136. Right. The remaining numbers you need to figure out is 3, and you know 3 is just going to be 2 plus 1, and therefore you just stick those two guys at the end here. Okay. Right. You just keep subtracting powers of 2 until you run out of powers of 2 to subtract. Okay. All right. Similarly, for 58, it's even easier. The next powers of 2, so that's lower than 58 is 32. Okay. And then if you add 16 plus 8 plus 2 to 32, you get 58. So I don't really have to cross-check that much. Okay. Okay. So the binary values for 139 is this. The binary number for 58 in 8 bits, okay, is this. Okay. Just like before, we stack them on top of each other, right? And then you just start doing column, 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 right? 1 plus 0 gives you 1. 1 plus 1 gives you a 0 with a carry at 1. 1 plus 0 gives you a 1. 1 plus 1 gives you 0 with a carry, and so on and so on like that. And down here is hopefully the final number that you're going to have, right? Okay. Right. In fact, if you add all these numbers up with the right places, right? So this is the 8 to the 8th bit, so that has a value of 138 and 64, and then this will have a value of 4. This will have a value of 1. You punch in your calculator or just do it by hand. You add these numbers together, you get 197, and hopefully that's the correct number. Okay. Happy? You get to play around with this in your homework. Okay. Okay. So in order to do this properly, okay, we kind of always have to know the number of bits, right, represented by those ones and zeros, okay? One way you can figure it out is that, well, this has 8 ones and zeros, so therefore it has to be 8-bit number, okay? But what you're going to see is that, right, with 3 bits, you can represent a unsigned, meaning it's always going to be positive, up to 7. With 4 bits, you're going to get 2 to 15, right? And then 8 bits can represent a number up to 255, okay? And notice the pattern here is always going to be, so this is 2 to the 3rd minus 1, 2 to the 4th minus 1, right? And this number is 2 to the 8 minus 1. So in general, okay, if you have n bits number, right, if it's an unsigned integer, you can represent it up to 2 to the n minus 1. Okay? You always lose one number because you always have to deal with 0. Okay? All right. So in your computer, the way a lot of our operating system works is that we use a 64-bit operating system. So if you take 2 to the 64, and then minus 1, of course, you have to do that, you get 1.8 times 10 to the 19 minus 1. Okay, so that's the biggest number. If you were doing a little bit of programming, you're going to see that if you try to enter in a number that's bigger than that, you actually have to um, do something special to represent a larger number than that. Okay? Okay. Minus 1. Okay. All right. So, any questions about just regular, well, positive binary numbers so far? This familiar? You guys seen this before somewhere else? Or just, know it yourself? Okay. All right, now we have to deal with negative numbers. So a lot of you got, except for maybe the CS people, may not have dealt with negative binary numbers before, okay? So one thing we can think about is that, well, if we have to deal with both positive and negative numbers, a solution to this is just maybe, I mean, positive and negative is a binary state, right? A number is either positive or negative, right? There's no in between the two, okay? What you can do is that, well, instead of representing my 7 as a 3-bit number, what I can do is just add an additional bit to represent the sign, right? Okay, where 0, 1, 1, 1 represents positive 7, 1, this represents being negative, 1, 1, 1, 1 means negative 1. Sorry, negative 7. Okay. All right, so, so if we were to make a map, and this is how I like to do a lot of stuff, especially in binaries, that, well, if I want to represent, 0, you get 0, right? If you negate 0, right, negative 0 is 1, 0, 0, 0, okay? And we're going to have to deal with this in the future, okay? Because that's the technology we're dealing with, right? This row just tells you something is positive or negative, okay? So obviously, let's say 5, right, is 101, that's positive. But if you put a 1 in the sign term here, this is the sign bit, right? Right? Then 1, 1, 0, 1 represents negative 5 instead. Is that clear? Especially those of you guys in physics who may not have seen these before. Okay? You're just making the first bit, right? Or also known as the most significant bit, the sign. Okay? Okay? If it starts with a 1, it's always a negative number. Okay? Well, we'll see how this works. Okay? So, one of the things is that any numeration you use has to still work with the math, right? Because we still need to do math. Okay? One of the properties of numbers or negative numbers, it has to obey, because when you subtract two numbers, it's the same thing as adding a negative of the second number, right? So a minus b is the same thing, should be the same thing as a plus minus b. So let's see if this works, right? I don't know why this stuff is popping up on the side, okay? All right, so let's do our, instead of 5 plus 7, let's do 5 minus 7, right? So 5 minus 7 should be the same thing as 5 plus negative 7, right? Okay, and you're going to see the answer, it doesn't work, okay? But let's go through the exercise anyway, okay? So 5, right, is 101, right, with a 0 in front, with a sign bit of 0, okay? Negative 7 has a sign bit of 1, right, because it's a negative number, and then 7 is just 1, 1, 1, okay? So you add these together, you get 1 with the carry, sorry, you get 0 with the carry, right? And then you add this column, you get a 0 with the carry. You add these three together, you get 1 with the carry, right? And you add these together, you get a 0 with a carry. So we should have put an extra thing here, right? 0, 0, right? So our result came out to be 1, 0, 1, 0, 0. Okay? Okay? since it starts with a 1, it's supposed to be a negative number, right? Okay, but it is not negative 2, right? Hopefully you guys know that 5 minus 7 is negative 2. So the math is wrong, all right? So you cannot do any computation with this, right? So this is a bad negative sign scheme, okay? What we're going to do is we're going to do this thing called complementation, okay? Back in trigonometry, when you have a, let's say, an angle, right? Let's say I have an angle that's like 45 degrees. Do you guys remember what the complement of 45 degrees is? This line. And you're in 35, okay? Right. It's a similar logic in here, but much simpler. The complement of a 1 is 0. The complement of a 0 is 1, okay? It's kind of like a way to always kind of complete the line or something like that, right? Except instead of 180 values it can only take ones and zero, okay? Because here's the actual example in binary. What's the complement of 0 degrees? It's just 180, right? Because the rest of it is 180, okay? Similarly, in binary, right? If you have a binary number 0, well, what I'm going to do is, so this is the sign bit, okay? The binary number for 0 is 0, 0, 0 with a sign bit of 0. The complement of that will be just all of these bits flipped, okay? So it flips to 1, 1, 1, 1, 1, okay? And it's perfectly legal because right now we have 1 and the sign bit, right? It does that automatically. So because all of the positive number will have a 0 here, right? When you do this complementation, right, when you flip all these bits, you flip all these sign bits to 1 also, right? It makes it negative by already. So that's nice, okay? But, right, the numbers now don't really match up with each other anymore, right? In fact, who can tell me, except for the computer science people, how do they match up? What does 0 match up to if you don't look at the sign bit? It match up to 7, right? Okay. So one thing you can think about this is that this is known as the ones complement. We're going to tell you about what two's complement is. The way you think about ones complement is that you count from 0 to 7, and then you count from negative 0 to downward to negative 7, okay? Because instead of the numbers going up, right? So this number goes up, goes up, goes up, goes up, goes up, right? You start at negative whatever, you start at 7, sorry, at 0, at negative 0, and you go down instead. The numbers are these values here are decreasing, okay? Just a way to think about it. You don't have to, right? Okay? But, okay, until, all the bits except for the sign bits goes down to 0, right? So 1, 0, 0 actually represent negative 7 instead. Okay, now let's check if the math works, right? Same example, okay? Okay, so in one's complement, this is known as one's complement, while positive number doesn't change, right, stays the same, okay? 0, 1, 0, 1, okay? Negative 7 is actually represented by 1, 0, 0, 0 instead, okay? Okay, so let's add these two numbers together. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. Okay, now you can either do the computation yourself, or you go up here and look at the table, right? 1, 0, 1, sorry, 1, 1, 0, 1 is this line here, right? And that's equal to negative 2. Is that the right answer? Right? So math still works, and that's what we want. Okay, let's do another check. Let's do two negative numbers. Okay, okay. Let's do -3 minus -4. Okay, just to make things complicated. In other words, you're just adding -3 plus 4. Okay, okay. -3, right? That number, right, has to start off with a 1 in the sign bit. Okay, and 3 is not right. Yeah, yeah. Let's cross this part out. I'm gonna do this over again. That doesn't make sense. Okay. Oh no, no, no. It is right because I'm counting the wrong way. Yeah, -3 is what the heck is it? -3 is right. You have to do 3, flip all the bits, right? Okay, -3 is 1, 1, 0, 0. Okay, so let me just do this once because I forgot it too, right? Okay, so the way you figure out -3 is you figure out what 3 is first, right? In positive. Okay, 1, 1. That's positive 3, right? That's 1 plus 2, right? With no sign bit. Okay, then you flip everything, and this is -3, right? This is positive 3. I see that? So this is the complement, the comp part. Okay, all right. So this is indeed -3. Okay, positive 4 I can deal with. Okay, it's just 0, 1, 0, 0. Okay, all right. Add these numbers together: 0, 0, 1 plus 1 gives you a 0 with a carry, right? 1 plus 1 gives you 0 with a carry. Okay, right? So here this is actually sort of interesting, right? Right, we're adding two numbers together, okay? But then there's an extra bit that came out, right? Right? If you're doing this computation on actual electronics, this will just get ignored, right? Because there's nowhere to store this information. Okay. All right. So that if you put 0, 0, 0, 0, right? Right? That's going to give you 0. But then this 1 kind of wraps around to the least significant bit, basically giving you 1. So this works if you do this wraparound thing where the the last digit that you don't have a space for gets carried around to the beginning. Okay? And this is basically how people built computers until the 1960s. Yeah, Shane?
So it's just a little unclear to me. Where's the 11?
11 is, so pretend there's an extra place here. Okay, I should have probably just put that in. Even though there's not supposed to be a place, that's why I didn't put it. Okay, there's just an empty column here, right? Right, these are the ones that line up with each other. Okay, so 1 plus 1, right, gives you a carry of 1, right? And then 1 plus 1 plus 0, right, gives you a carry of 1 still, right? And this little last digit here, that's this extra digit, right, gets carried.
Come from the 1 plus 1?
Yeah,
Okay.
well, yeah, 1 plus 1 gives you always 10. Well, 1, 0. Let's say 10, right? Okay. Um, what's a good example of that? Just like 5 plus 5 gives you 10, right? There's always a carry. Okay. Right. And this digit, if you make all the wire connection correctly, gets held by the least significant bit. Okay. So this is actually the LSB. Okay. Which goes here. Okay. And that gets you the right answer. And in fact, people have made this work. I don't know. I don't know how long digital computer has been running since the 1930s, right? Or there have been sort of computers, right? Okay. All right. And in this representation or this numeration, right, we can represent numbers that's 2n to the minus 1 negative to the 2n to 2n minus 1 to the positive, right? By having this extra bit, okay? Where n is, the values bit plus the sign bit, right? So this is, in this case, this is a 4-bit number, right? That can goes from -7 to +7, okay? Right? So there's a problem. Well, people, there's an interesting quirkiness to it. Let's not call it a problem, because this still works. All the math still works, okay? Okay? There are two zeros, okay? Right? There's a +0 and a -0, okay? This might seem like a small problem, like, you know, for us humans, like, oh yeah, there's two zeros, let's just deal with it, right? For a computer, if you reach two different zeros and two different calculations, it thinks it's two different numbers, right? Zero no longer equals zero, which is troubling. Because zero is actually a very important number, right? Those of you who have taken a little bit of like histories and math and stuff like that, right? Invention of zeros, right? Basically revolutionized math, okay? Okay. So until the 1960s, people used ones complement. In fact, there was still a computer in the 1980s called the UNIVAC. So the vac means vacuum tubes, right? Not transistor yet even, right? This was still being made in the 1980s. Okay, people use the ones complement. Okay, so but in our computer, the ones we're sitting in front of, okay, use this great idea called the twos complement, and guess what that's going to be? Okay, all right. The twos complement basically does the ones complement. So this is the same table I showed you before, you know, without that, right? Where, right, you flip all the bits, right, and then you get the negative number, right? So you still have a -0 here, right? In two's complement, you don't have a -0. Let's just get rid of that. Okay? There's no numeration representing -0. Okay? And all you do is you shift this down. Okay? That's the pictorial way to think about it. Okay? Right? The ones two's complement is the ones complement shifted over down by one row because you want to just skip 0. Right? You want to skip -0. Okay? Okay? Because you don't need two zeros. Okay? So, so the method to deal with this is that, let's say I have, let's just do some examples of this, because this is usually sometimes confusing. Let's say I want to represent, oops, not highlighters. Say I want to represent highlighters. Come on, be nice. -5, right? The first thing I do is I write +5, which is 0, 1, 0, 1. Okay? That's +5. Okay? Then I do the complementation. Okay? Complementation means I flip all the bits, right? 0 becomes 1, 1 becomes 0, 1 becomes 0. Sorry, 1 becomes 0, 0 becomes 1, 1 becomes 0, 0 becomes 1. And now I know this is a negative number because this is the sign bit, right? Great. That's the ones complement. Okay. All right. Then what I do is I I basically add 1. Well, I add 0, 0, 0, 1 to it, okay, depending on number of bits, okay? So, in order to represent this, what I have is going to be 1, 0, 1, 1, okay? And hopefully that matches up with -5, right? Yeah, down here, okay? So that's the method in general. You know, you don't want to make this table for 64 bits, right? Okay, okay. Everyone clear how you do this, right? You figure out what the positive number has to be. Complement meaning flip all the bits, okay? And then you just add 1 to the end of it, at the end, okay? Okay, right? Notice now we can actually represent more numbers, well, more negative numbers, okay? And those of you who deals a lot with computing might notice this. You can actually carry one value more information on the negative side of your integer compared to your positive integers. Okay, because you can represent 2 to the n numbers on the negative side, but then only 2 to the n minus 1 number on the positive side, right? Okay. All right, so let's check math, right? Remember, all this stuff has to obey math, this little weird thing that we try to do all science on. All right, let's do 5 minus 7 again, okay? So negative 7 is this number here. Let's do that in green highlight, right? And then 5 is still 5, right? 5 is just 101, okay? Add these two numbers together, right? 1 plus 1 is 0 with a carry of 1. I guess that carry of 1 is supposed to be over here, okay? All right, 1 plus 0 is 1 with no carry. 1 plus 1 is 1 with no carry. 0 plus 1 is 1 with no carry. Okay? We go back up here. Look at 1, 1, 1, 0. What does that number represent? Sorry, what does that numeration represent? Always mix these two up. Okay, it does represent negative 2. You see how that works? Okay. All right, let's do one more. Okay, 4 minus 3, hopefully I did this correctly. Okay, is equal to 1. Okay, 4 is 0, 1, 0, 0. 3, if you look that up on the table, is 1, 1, 0, 1. Add these two numbers together with all the carry and stuff like that, you end up with 0, 0, 1, sorry, 0, 0, 0, 1. Okay, it even do the sign bit correctly. You see that? Right? We know it's a positive number, right? So it should always have a 0 in the beginning, right? When it's a positive number. Okay? And in fact, 0, 0, 0, 1 is equal to 1 in decimal. Yeah?
So why didn't the one, the carry of the one at the end get carried over to the beginning like it did in the other problem?
Let's see. I think it did, right? Oh, no, it didn't. Huh. So yeah, the two's complement also, I think, fixed that problem where you have to carry the last one over to the front. Okay? Yeah, that's a good point. So I didn't skip that. Okay? Right? So in this case, in the two's complement case, you just throw this away. You don't have to carry it around anymore. Okay? All right. I think I already went through the process where if you want to do the two's complement of something, you take the decimal number, you converted it into the binary first. If the sign bit is 1, then you switch all the 1s to 0 and 0 to 1, and then add 1 to it at the end, okay? Right? The conversion is the difficult part in 2's complement, right? But then the math is the same still, okay? Right? So let's do another example where we're converting negative 6, okay? So in binary, positive 6 is 1, 1, 0, right? With a sign bit of 0. We flip everything, so that flips everything over, okay? All the 1s become 0, all the 0 becomes 1, okay? And then you add 1 to it, right? Adding this 1, right, gives you a carry in the 2's place. You see that? You still have to add that properly, okay? Okay. Another way to think about it is to think about the sign bit has a weight of negative 2 to the n. What the heck does that mean? Okay? Same number, negative 1. Instead of thinking about it as a sign, this number, this place is equal to negative 8. Okay? Right? Okay? Because remember, this, the n here is 4, right? 2 to the n minus 1. Ooh, 2 to the 4 minus 1, right, is 8, right? So therefore, this place here, this last place here, has a weight of negative 8, okay? And then if you just add these numbers up, negative 8 plus 0 plus 2 plus 0 gives you negative 6. It's another way to think about it, okay? You don't have to do it that way, you can always just do the do that process. Okay. Okay. Um, and one of the first two's complement computer was also built in the 1960s, and it's based on vacuum tube. That's why it's the size of a room. Okay, this is before transistor is really like commercialized, where a lot of people can use it. Okay, and apparently there's like a no smoking sign in front of it for some reason. Okay, all right, how much time I got? What time is it?
247.
2:47. Okay, so 10 more minutes. Okay, so as we saw before, a lot of times when you add two numbers together, there's an extra bit you have to hold, right? Sometimes because, like, if you add 7 plus 7, right, that's 14. You added two 3-bit number together, it makes a 4-bit number, right? Okay, okay. So, yeah, that's just me copying the table. So if we, yeah, let's say we're doing 4 plus 5, right? Right, 4 is in binary, so these are in decimal, okay? 0, 1, 0, 0. And then 5, right, is 0, 1, 0, 1, right? The result of that is actually going to be 1, 0, 0, 1, right? Because this bit represents 4, this one's 4, this one's 1, right? That's how I got those numbers. To get to 9, right, I need something in the 8th place, okay? Okay, and therefore, so you have two, this is a 4-bit, go away, 4-bit signed integer, right? This is a 4-bit signed integer, right? This creates a 5-bit signed integer. See that? Okay. So when you're adding two numbers together, right? Let's say you're adding n bit ugh, n bit plus m bit numbers together. Okay. The results is always going to be the greater of n and m plus 1. Okay? So if n is 5, m is 7, right? Whatever result you're adding is going to be, did I say 7? Yes. It's going to be 8 bits in order to hold it. Okay? Okay? There is a way, so since all of our operating systems are 64 bits, okay, there is a way to catch overflows. So whenever you go over the number of bits you're supposed to, it's called an overflow error. Okay, let me just look up what the example I'm using is. Nope, not here. Example. Lecture. Okay, okay. Yeah. So let's say I have two numbers, a plus b equal to c. Okay, it doesn't matter what the number is. So if a is a 3-bit number and b is also a 3-bit number, okay, right? Then you can make sure that, well, C is going to be some 3 plus 1-bit number, right? Or another word, 4 bits, okay? Okay, right? So you always add this extra bit to it. And you can check this, okay? Because, right? Right? We know that 4 and 5 are both positive numbers, right? Right? 4 is greater than 0, 5 is greater than 0, right? Whatever the result is has to be positive, right? Okay? Right? So, because what happened is that if you just add this without thinking about the overflow, this will result in a negative number. If you don't have this, 4-bit to hold to hold the extra bit. Okay. All right. We're not going to try to implement this, but just to know that, this is a way to cache these things. Uh, let's see. Bit grouping. Okay. So the last thing I'll talk about is, there are, besides bits, uh, people have these words called crumbs or tidbits or TAS. I don't even know what that is. It's basically 2 bits. Okay. So if you have a number that's 00, 10, or 11, this is called different crumbs that you can have. Okay, and then if you have 4 bits together, because it goes up by powers of 2, of course, right? It's called nibble. Okay, 5 bits is called a nickel, because a nickel is 5 cents, right? And hopefully this will be familiar. A byte with a Y, right? That's 8 bits. That's usually how people represent, storage and memory and stuff like that. Um, 10 bits is a decal, a platy, a diner, and a word. How many of you guys know the size of a word on your computer? I don't expect, maybe you guys know this. I think at least on a Windows computer, is 8 bytes. Okay. Um, a word is basically a character in your computer. So instead of representing a number, it represents a character. Okay. A, B, C, D, E, F, G. Okay. Um, okay. And this actually depends on the computer architecture of the operating system that you're using. Okay. That's why I say, oh, for your computer, how big is a word. Okay. So when you type a 500 word essay, it's 500 times 8 bytes that you're going to be storing in your file system. Okay, and that's how they figure that out. Okay, I think that's all I want to cover today on binary numbers. Sorry, it's a little bit slow, but it's just to get everybody at the same level about binary numbers.